right, let's go ahead and get into some homework. So the first thing we're going to do is work on a couple free response questions, and then we'll do some multiple choice at the end. So just like we went through in our examples of this section, we're going to focus on identifying when functions are continuous or not, as well as identifying the discontinuities, and then finding the value k that's going to make the function continuous. So let's go and look at this one. We recognize this is not a continuous function. That is a rational function. So, well, I guess it could be continuous, but we know that it is possible for us to have some discontinuities. So the first thing I'm always going to do a rational function is look to simplify it. So I can't really do anything in the numerator, but I can factor out an x in the denominator. And that's going to give me an x squared plus 1. Now, x squared plus 1, that's going to be continuous for all values, but you can see that these x's are going to divide out, so that's going to leave me with a 1 over a x squared plus 1. So there's no real numbers that are going to make my denominator undefined from here, but you can see that I have a whole. Since these x's divide out, that is a removable discontinuity. So I can say this is discontinuous, and there's a whole at x equals 0. All right, the next example, again, we want to see that's continuous and that's continuous, right? It's two quadratic equations. So they're both continuous. So we want to see, are they going to be connected at 0? So what I'll do is, let's just say, all right, x squared plus 2x has to equal a negative 3x squared. And we'll just plug in 0. Well, guess what happens when you plug, well, let's just show our work. Plus 2 times 0 equals a negative 3 times 0. So I get 0 equals 0. Now, most students will say, hey, that's awesome. Look at that. Like 0 is equal to 0. But go back to the restrictions. The restriction says this function is only true for x values less than 0. This function is only true for x values that are greater than 0. So the important thing that I want you to see is none of them are defined at 0. Nothing is defined at 0. So I don't know what this graph, looks like, but I would probably beg that it's going to look something like this. There's an undefined value at 0. And it looks something like that. So the reason why this is important is that's a whole. So this is discontinuous. And again, we have a whole at 0. So it's a little different than that whole, but you can see it's kind of the same idea. All right, the next one is we have a function sine of x where x cannot equal 0. And then we have negative 1. So let's just go ahead and graph what sine of x would look like. Right? If you remember the sine of x function, it's basically true for all values except at 0. And if you remember the sine of x function is at 0, 0, and then it looks something like this, right? And then it goes on there. But then it says it's equal to negative 1 at 0, right? So we have that little dot basically there. So again, you can see that there's like break in the graph, right? There's a hole, right? It's undefined there. And even though it is defined here, there's still a break in the graph. So it's still discontinuous. And guess what? It's another hole. So there's a hole at x equals 0. So all three of these are ways that we can obtain that you can see that holes can be obtained. All right, let's look at the next example. Looks like there's a lot going on in this function, but in reality, it's just the square root function, right? And it's just being shifted to right, being shifted up 1, being reflected about the x-axis, and it's being vertically compressed 1/3. But again, if you look at the parent graph, like I don't care what I do to this function, right? Here's the parent graph. That is square root of x. I don't care what I do to this function. If I flip it and stretch it, compress it, whatever, there's no breaks or holes. Even though it's not defined for all real numbers, it's defined for every value on its domain. So therefore, this is a continuous function. There is no breaks. You can draw this graph without lifting up your pen or pencil. If you remember the tangent function, so tangent function plus 1, again, that is just going to be shifting the graph up 1. But remember, like what is tangent? Tangent you're doing sine over cosine, right? You're dividing by cosine of equal to 0. So if you remember, the tangent graph, right, has these asymptotes. And it occurs, if you remember from the unit circle, at pi halves. And the distance between these two asymptotes is going to be pi. So we can say that this is discontinuous. And we can say there is a asymptote at x equals pi halves plus pi n. And it's important to recognize that this graph is going to continuously repeat. So we want to represent all the asymptotes, unless we are asked something different. All right, the next example looks like that's the reciprocal function, right? You can see again, we have another rational, function here, but we have some transformations. It's actually a part of the parent graph reciprocal function. So again, I'm going to be looking for asymptotes and holes, and nothing's going to divide out here. But what I do recognize is that that there are going to be values when my denominator is going to equal to 0. So let's go ahead and solve when those values are. So a lot of students will just choose 3 because they're like, oh, I see a 3. But again, you want to find the values that make your denominator equal to 0. So I'm actually going to set my denominator equal to 0. And there you go. X equals 3/2. So again, the plus 4 isn't really changing anything. All that's doing is just shifting the graph up 1. So this is a discontinuous graph. And we can say there's an asymptote at x equals 3/2. All right, let's get into the next example, which is going to be determine the value c that makes the function continuous. And I don't know why I use c because it's actually the value k. But again, sometimes we'll use different letters. So in this example, all we're simply going to do is set the two equations equal to each other and then solve for k. All right, and then again, we're going to plug in our values where these two functions could be connected or not. We want to find the value at -1, so we're going to plug in that value from our restrictions in for x, and then solve for k. So we have -2 plus k equals 3, and then we're just going to add a 2 to both sides. K equals 5. All right, over here, again, you can see kind of a lot going on here. So let's set it all equal to each other. And that equals x squared minus x plus 2k. Whew. All right, and again, we're just going to plug in our 1, right? So we have a 1 squared plus 1 times k plus 1 equals a 1 squared minus 1 plus 2k. Okay, so that's going to be 1 plus k plus 1 equals a 1 minus 1 plus 2k. All right, so 1 minus 1 is 0, right? 1 plus 1 is 2, so 2 plus k equals 2k. And then we can just subtract. So what do we get here? We get 2 is equal to k. Voila, there we go. All right, so now let's go and get into the multiple choice portion. And we just have only 4 of these questions. So question number 1 reads, suppose that the function f is continuous for all real numbers and that f of x equals x squared minus 4 divided by x plus 2 when x cannot equal -2. So find the value of -2. This continues for all numbers, and that when x is equal to -2. Okay. So in this case, what we're going to want to do is, again, simplify this. So if I simplify my numerator here, I get an x minus 2 times x plus 2 divided by x plus 2, right? Now you can see that, well, actually, I can simplify this. So that equals x minus 2. So then if I want to plug in f of -2, right, that was it. F of -2 equals a -2 minus 2. So -2 minus 2 is a -4. Answer A. Question number 2, it says find the intervals on which the function is continuous. Okay, so basically we want to see where are there going to be asymptotes or holes. That's going to break up the graph. So again, we're going to want to simplify this. So we have x plus 4, and then in this case, we're going to break this up into a, let's see, factor this would be x minus 8 times a x minus 2. Okay, doesn't look like I can break anything up. So this graph is going to be undefined at +2, and this looks like there's an asymptote there, and 1, 2, 3, 4, 5, 6, 7, 8. So it looks like it's going to be, I don't know what this graph looks like, but I know it's going to be from -infinity to 2, right? So that's going to work. That one works. It's going to be from 2 to 8, or 2 to 8. Why is these not showing up? 8 to infinity. I think that's written wrong. There you go. That should be 2 to 8. Yeah, because that's how, like, that's all crazy. 2 to infinity. I think that one was written wrong. That was -2 to 8. Yep, so it should have been 2 to 8. So anyways, the answer is B. Sorry about that. Question number 3 says, find the vertical asymptotes of the graph f of x. All right, so we're looking at secant graph. Well, what the heck does secant graph? Remember, secant is the cosine, is the inverse of the, no, it's not the inverse. Sorry, it's the reciprocal of the cosine graph, right? So we got to remember when does, and actually, you know, you got to remember the secant graph has these asymptotes here. So what we want to do is find, well, when are these asymptotes going to occur? Where did these asymptotes occur? Well, these asymptotes occur. These asymptotes are going to occur when cosine is equal to 0. So let's go and look at the unit circle and say, all right, when is cosine, the x coordinate, equal to 0? And you say, oh, it's going to be there and there, right? So you could say it's going to be at pi halves plus pi n. And it kind of just like the tangent function, it's actually the exact same from our tangent function. So pi halves plus pi n. And you can see that, right? Because that's pi halves. And then it's going to occur right there. So if you add a pi, it's going to take you to that function. So our answer is A. All right. And then last example, it says determine the points of discontinuity. Whew. All right. So, so again, these are going to be where the graph is going to be broken up. And so you can't divide by 0. So that's a point of discontinuity. And you cannot divide by 4 because that would make your denominator equal to 0 as well. So therefore, there's going to be 2 points of discontinuity that is going to break up the graph. And that's going to be at 0 and 4. So there you go, ladies and gentlemen. That is it for your first homework assignment. Hopefully this was helpful. And I look forward to seeing you in the next lesson. Cheers.